Hi, good morning and welcome to the ZP Developer Zone. So we do this webinar every Thursday at 8 a.m. London time, and it's really just to sort of answer technical questions that have come in during the week. So the first thing I want to do is essentially just dive into it. And it's worth saying that we have our ZP Academy. So if you're looking for a couple of free courses, then we do have our ZP Academy. There's also Academy courses on things like CGM, continuous glucose monitoring, biosensor manufacturing, etc. So we have an Academy, and we have this webinar. We do it every Thursday, 8 a.m. London time. We have collaborations. I've recently put up so that we've had a collaborator come in and work with us, which was great. We offer jobs. We have our ZP Developer Zone website, and we have our workshops. So if you're looking for free technical information, I would look at the Academy. If you have technical questions at Zimmer and Peacock, send them in to us and we'll try and answer them during this webinar. I just want to say good morning to Aftab. Aftab is online this morning and he is our representative in India, so it's nice to see you. We have our webinars, collaborations, Developer Zone and workshops. It's probably worth saying that ZP does have a workshop titled Continuous Glucose Monitoring and Wearables Biosensor Workshop. This will be happening in Norway in September. Here's a link to it. Hopefully I've also, any link that you see today, I should have also put the link also on under the video as well, so you should be able to find that as well. So we do have workshops. There is a workshop being held in Norway, and you're welcome to sign up for that. Now the questions we've had this week, we've had an awful lot of questions, so I'm going to sort of go rather quickly. We tried to do this in 30 minutes, so that would mean something like 4 minutes, 4.5 minutes a question here. But electrochemical impedance spectroscopy. So we have had an inquiry that came in to us, came in via LinkedIn asking about impedance spectroscopy. I'll touch on that. Another inquiry came in about nitric oxide sensors. I'll touch upon that. Also another inquirer had asked about testosterone sensors, and I failed to answer it in another webinar, so I will cover that today. We had an inquiry about screen printed electrodes, another inquiry about glucose strip manufacturing for university laboratories, so I'll talk about that. An inquiry came in about wearable sensors, and in particular cortisol sensors. And then the last one that I almost overlooked was how to connect to a ZP pH sensor, so I'll also touch upon that today. I will talk rather quickly because I'm just conscious of the time. So the first one is on electrochemical impedance spectroscopy. Just to say, look, we do have a couple of videos. I said earlier on, take a look at the ZP Academy, but also there are a couple of videos for free. If you take a look at our knowledge base and our educational videos, you will find a couple of videos there that will also be, let's say, useful. Now, regarding this charge transfer resistance, this RCT, so the inquiry was this. This person's built themselves a sort of an immunosensor type sensor. They're using it in what we call a Faradaic mode. There are two modes, Faradaic, non-Faradaic. I will define that. Their problem is that when they add analyte, they get a change in this this RCT, this charge transfer resistance, but they also get it when they just add buffer. So, I mean, the simplest thing is it doesn't sound like it's working, but let's try and dig into this a little bit more than that. So what's happened is they've probably got something like a gold electrode. I would just want to say morning to Hitcham. Nice to see you this morning, Hitcham. So they've probably built on a gold electrode something like an immunosensor. They get their, they have their antibodies on the surface of it, and the antigens bind to that. And because it's Faradaic, they have a sort of reporter molecule in there. Now, what I suspect is that they have, as the antigen essentially binds, the RCT value. Now what I'm showing here is the Nyquist plot. I know it's it's unfair to throw in this electrochemistry. Take a look at the ZP Academy, or take a look at the couple of videos that I referred to on the previous slide just to get a sense of what maybe the Nyquist plot is. But the Nyquist plot in some ways is a spectrum, and they got a spectrum of this, and it has a value that they can extract called the RCT. So the hypothesis and their confusion is that RCT is in the end proportional to the amount of antigen that they're binding in this immunosensor. But they're finding that they do get a change in RCT value, both when they add the antigen and when they don't add the antigen, just with buffer. So I know the glib answer is, well, it's not working. First of all, I don't think they're necessarily on ZP electrodes, and I could be wrong on that. You know, so it's hard for me to understand necessarily what's going wrong here. I do want to say that this kind of approach can work. You know, here's a ZP gold electrode, a ZP value electrode. First thing I want to say is we've actually made an entire immunosensor on top of this sensor, and then we've tested it. And I think you can actually see the quality of our screen printing, because this is 5 nanograms per milliliter, 25 nanograms per milliliter, 50 nanograms per milliliter, 75 nanograms per milliliter. These are very small amounts of material. You know, when you think about glucose, it's 5 millimolar. It's so high in concentration. So we're actually getting good discernible signal even at these very low concentrations, and it sort of really tells you something about the quality of our screen printer on those electrodes. But the reason I'm bringing this up is when I look at our data, whoops-a-daisy, we have almost a signal that there's an RCT value here, which is almost like the diameter of essentially these semicircles. This increases when you go from green to sort of this pinkish, to this lilac, to this yellow. The diameter of the semicircle, which is the RCT value, is essentially increasing with concentration. So it's to say that I know this person's having problems, but actually it can work. And you know, so first of all, let's establish that in theory this kind of work can work. I would say this, that if you're doing this kind of work these days, whoops-a-daisy, if you're doing this kind of work these days, I wouldn't necessarily go for gold anymore. Gold prices are spiraling. You should really go for carbon. There's a paper that I've referenced in the past. Just have a quick read of it. I'm not going to dive into it, but I have done lots of videos on this. And so you can make immunosensors on carbon electrodes, and I would encourage it because the price of gold is also spiraling. If you are going to do this kind of work, I will go back to the question in a minute, but if you are going to do this kind of work, you'll need an impedance spectrometer. I've put a link under the video. You will need connectors. It's funny how many experiments you have strange values because actually your connections are not good. So you do need good connections, and you do need a screen printed electrode that you believe in. These carbon electrodes that we do, you know, I think they really are the world's best. I've said this before. HitCham's online this morning, AFTAB's online this morning. They've heard me say it. The biggest consumer of ZP electrodes is ZP. And that means that it really helps keep our quality high, because you know, we know before anyone else knows if there's been a problem, and we don't send the problems out the factory. So their problem was this, that even the buffer causes a change in RCT value. So this whole idea that as I add antigens, this value here increases, that seems to work, but it also seems to happen if they just add buffer. And so the simple answer is, maybe the equivalent circuit that you're using is not as simple as you think it is. So this is an equivalent circuit for one of the sensors that we've built. You can see the sheer number of elements that we have in here. This is the solution resistance. In fact, I've got it. You know, this is the electrolyte essentially, the solution. This is the linker, so the capacitor and resistor due to the linker, and this is the antigen. So you could have a couple of things. You know, you could be getting an increasing R3, but a decrease in R2. And it's essentially sort of hiding your signal, because if one increases, the other one decreases. These probably both, if you use what's called a Randall circuit, they're probably both, they're both summed together in your particular circuit. So you might just actually be using the wrong equivalent circuit. So, you know, the simplest thing is it's not working. I understand that. You could try fixing it by saying, all right, you know, change your supplier of screen printed electrodes. If you're using gold, try carbon. If you're using carbon, try gold. And really, is your circuit, equivalent circuit, the RCT value, are you using a very simple Randall circuit, or are you using something more complicated? Because in this circuit, I could easily see that, as I say, if R3 goes up and R2 goes down, then it's going to start confusing you. But if you had a more complicated equivalent circuit, you might be able to separate those two elements out a little bit. So it is hard, obviously, to just receive an inquiry in text and then translate it into into the AHA solution. But I would take a look at supply of electrodes. I would take a look at trying carbon if you're on gold, or gold if you're on carbon, and I would actually think about a more complicated equivalent circuit. Clearly, your one is not explaining the phenomena that you're seeing. And as I say, this is actually one of the equivalent circuits that we've used in order to understand our data on occasions as well. It's also probably worth saying, at Zimmer Peacock, when we're doing this kind of work, it's not just in labs. We are generally working in class 7 clean rooms, and we are ISO 13485. So, when we're doing this kind of work, there's an entire team behind it, and it is hard sometimes in academia to be able to replicate what we can necessarily do in industry, because the budgets are just so very different. Now I'm going to slightly change gears now and say that's a hard one, that RCT question. I'm going to talk now about nitric oxide sensors, so NO sensors. So we got a question in. It says they're interested in purchasing, which is always nice. They want to know essentially the range. They say here the detection limit, but I'll talk about the range. They might want to use it in different pHs. Now I'm going to talk about the sensor itself, and then I'm actually going to talk about testosterone sensing. But when I go into testosterone sensing, I'm going to talk about the hardware you need. So I will talk about the sensor, but then part of my testosterone sensing answers will also be applicable to this person as well. So first of all, let's dive into the sensor itself. So on our website, there's a YouTube video on this website, and there's also a page about it. And sort of on there, I do have some data. Now I realize now that data is it's a little blurry. I did try looking for the raw, let's say, graphs behind it. So I haven't found them, but I will explain what's going on here. So they were asking about the range. And so when I look at this, we start off by testing 0 micromolar. So along here I have 0 micromolar. Then the first test we run is actually at 10, 20, 30, and then then we're sort of getting close to 40, and we go up to about 80. So we're testing in that range, but you can see a clear differential between 0 and 10. That doesn't tell you that that's the limit of detection. It just tells you that I have some confidence that we can distinguish 0 from 10. The reason I'd say, because you actually need quite a lot of data to calculate the limit of detection. Limit of detection is statistical analysis. Yeah, I'm just getting a really nice feedback from Hitcham as well. Hitcham's online. He's just talking about the RCT thing. So thank you, Hitcham. Yeah, it's complicated, but thank you for the feedback. So back to the nitric oxide sensing. I can tell you that the range that we test in is 0 to 80 micromolar. I can tell you that the pH we test in is pH 7.2, because we are often working sort of, really we're thinking about human health a lot. Now that means our sensors can actually be used in non-human health applications, but that means that, by default, when I'm mostly talking now, I'm actually thinking about pH 7.2. We haven't tested outside of that, of those others. Now I am going to go on now to talk about testosterone, but I am going to talk about some hardware which actually will also work with this sensor as well. So quick answer is we've only tested pH 7.2. We've tested in the linear range 0 to 80 micromolar. I can see a good differential between 0 and 10 micromolar. I forgot one part of their question was, how do they make standard solutions? Nitric oxide is a really hard analyte to work with. I have worked with nitric oxide in a professional capacity before Zimmer Peacock and during Zimmer Peacock. It is a hard analyte to work with. You have to get NO gas cylinders, or you have to generate NO in situ in the lab. It is hard. If you need, the easiest way to do it is to get NO gas cylinders, but it is a toxic gas. You have to do your you do have to do your cost assessments really well, you know, and do a risk assessment. So the quick answer is you can generate NO using chemical reactions. That's how we do it. You can also get gas cylinders. I've done that in the past. It's a dangerous gas, and you have to take proper precautions. It's not an easy analyte to work with because it's not intrinsically stable. You can't make a solution of NO, you know, and put it on the shelf and come back. It will have all gone. So it is tricky. We make it chemically. You can get gas cylinders. I gotta give you lots and lots of heads up. This is dangerous stuff. But we make sensors. We test sensors. We can work with people on it. But be careful when you're trying to deal with nitric oxide. All right, I've laboured the point a bit. Question number 3 is about testosterone. Right, first of all, so we have a testosterone sensor, and we have some data on the website about it. And the first set of data shows that we have a signal from 0 to 1 nanomolar. So this work was done in buffer. So let me just answer the question. You know, we did it in buffer, probably pH 7.2, and we do actually get a strong signal in the range 0 to 1 nanomolar. So we're happy with that. The next set of data that I've put out there is actually we've tested saliva of a female that we then spiked with testosterone and sort of tested it in saliva. So we wanted to prove if we could test testosterone in saliva, and we were happy that we were actually able to get a result proportional to concentration. So works obviously in buffer, it works in saliva as well because we were interested in doing that. This is the link to that particular website where I got the data from. The question really, this is also plays into the NO guy. How do you run these sensors? So we have, whether it's a testosterone sensor, whether it's the glucose sensor, whether it's the NO sensor, whether it's the pH sensor, that will also come up later on. We have something that we call OmniSense. You put the sensor in the meter, you put the sample on the sensor talks to the app, the app runs the meter, the data goes back to the meter, we upload the data to Julie. Julie is a bespoke cloud system which can hold electrochemical data, or rather, can host electrochemical data, process electrochemical data, allows us to share electrochemical data, or we can just process the data in so many ways, filters and AI algorithms. It's very powerful. So we have Julie. So for the testosterone, how do you run a testosterone sensor or an NO sensor? You have the sensors, the meter, the app, the Julie database. The raw data ends up going to Julie, and we do the calibration, and we can give you a value. So we have something called OmniSense. I've got a link to it, and it can be used in conjunction with, I want to say, just about any of our sensors. I've got to be careful with that because we've got over 30 sensors, so there possibly is a gap that I haven't thought of. Now, question number 4 was regarding somebody wanted to make some biosensors. They want to make some screen printed electrodes. They want to make them in high volumes, and this happens quite a bit, that people will send us a specification for a screen printed electrode. So I'm not going to discuss that specification, but I am going to discuss very quickly contract development, contract manufacturing of screen printed electrodes. So people come to us and say, can I have a custom screen printed electrode? We do have a sort of landing page for this. I've put the link underneath the video. They'll often talk about, there'll be a request. They'll then talk about tolerances, and I'll discuss here the importance of tolerances. They very rarely talk about inspection criteria. They often talk about screen printed electrodes in the absence of the entire technology stack. So if I was to use a glucose sensor, you often have a screen printed electrode area, or electrodes. You can have functionalization with enzymes. You can have the addition of microfluidics. Then you have the excitation of the electrode itself from the meter. Then you have the processing of the raw data into information. There's a whole stack of technologies, and so it's somewhat not correct to separate all that stack of technology from one another and just say, I want the screen printed electrode. And I'll explain what I mean by that now. Often, very rarely do people actually ask us to do electrochemical characterization of screen printed electrodes, but that's probably important. And then there's there's a commercial side to this, which is when companies on board with one another. So you get a request for a screen printed electrode. In these requests, people will often ask for a certain length, they'll often ask for a certain width, they'll often ask for maybe a certain thickness of substrate, but not all the time. And they might ask for a certain print thickness, and that's something that we can characterize at Zimmer and Peacock. We've done it several times, our print thicknesses. So these are kind of obvious things, and the kind of things that people request. I've just had so what I'm going to do is go in a little bit deeper now and say, that one of the things that people quickly forget in specifications is actually, have you considered roughness, for example? So, if the inquirer said, I want a carbon electrode, then my question would be, that's fine, we can, print that, and you can even print length and width, no probs. But did they also define the roughness of that? So obviously at Zimmer Peacock, we can measure do measure the roughness of our carbon prints, for example. And if you can have two obviously carbon electrodes that look identical, but if they're rough, obviously the one that's rougher will end up giving you more sensitivity than the one that's smoother. Whether that sensitivity is good or not, you can't just say, oh, sensitivity is great. There's lots of, there's a balance in life. But the quick thing is, people will ask us to, have tolerances and controls on things like lengths and widths, but they might actually forget to ask us anything about roughness. And so I think just giving a company a spec, I think you have to engage with them a lot more deeply, I would say. The other thing that comes up quite a bit is people will ask for, electrical resistance along these tracks. With electrical resistance, it's a rule of thumb is it's good to have, obviously, well, not good, it's good to have lower resistance. Higher resistance can end up distorting your signal, but it's also about consistency of resistance. If your conducting track is always 1 ohm, it's probably good to be generally in 1 ohm. In fact, with that answer, I'd actually say it's a bit like this, that if the resistance is 1 to 10 ohms, you don't really care. And the reason I make that statement is because the biggest resistance in your circuits is through the solutions. So if your sort of, resistances along these tracks are some less than ohms, less than some 10 of ohms, you don't really care that much. But people do ask us about electrical resistance, but they never ever ask us about functional testing. And what I mean by that is, this is an electrode that's going to be used in an electrochemical system. If you're going to do contract screen printing for someone, you probably have to talk about the outgoing quality control, which could involve doing some electrochemical characterization. So here I'm showing cyclovoltammetry, and because we have this proprietary system called Julie, we're actually able to gather data, for example, in our facility, and process the data very quickly and turn raw data actually into information. Now that is also something that, because it's cloud-based, it can actually run at other people's facilities as well. So, in order to do that, you need to have the ability to obviously manufacture screen printed electrodes, the ability to test screen printed electrodes, and then we can just upload the data to the cloud and process it. But you are asked to give electrical specification, but there's never an electrochemical specification. The electrochemical specification is probably more important than the electrical specification. So ZP, because obviously our background in electrochemistry, we do understand the electrochemical specification, which is not, never asked for. People do ask us about tolerances. Of course, we're very, I understand why people want these tolerances. The question is are tolerances important? And the answer is yes and no, and it depends a little bit. And I'll sort of explain that a bit. I mean, the obvious one is this, that if you're doing a potentiometric measurement, tolerances are not very important. As you do amperometric measurements, then yeah, they do become more important. But tolerances, if you put all of your, when you talk about the variabilities in a biosensor, you have the underlying electrode, then you have the enzyme layers, then you have the microfluidics on top of that. There's a lot of places to have variability in your manufacturing. And so you have to think of it holistically. You can't just put all of it onto the screen printed electrode. I suspect that, at ZP, I know this, that we make a very reproducible screen printed electrode. But then, of course, when you send these out to people, then the enzyme deposition step is often, variable, and that's the sort of source of variability. So tolerance is important. Don't overemphasize it, because actually there's lots of routes for manufacturing variability, and it's not always on the screen printed electrode. And I say it's a mistake to think of the screen printed electrode in isolation for everything else. So let's talk about the excitation, of sensors. You can do voltammetry, amperometry, potentiometry, and impedance spectroscopy. If I was making, for example, a modern glucose sensor, I would be using a mix of amperometry, I imagine, and impedance spectroscopy, and probably potentiometry, and actually, when I think about it, voltammetry as well. Once upon a time, when people made glucose sensors, the only technique they used really was amperometry and coulometry, because it's all they had. Nowadays, with modern electronics, you can actually do a lot more techniques, and so that whole point about tolerance in the screen printed electrode is, if you're just using amperometry, then it's probably more important to have tolerances in the manufacturing. But actually, if you're smart and you're using much more sophisticated techniques in the measurement, for example, of glucose, lactate, oxygen, testosterone, NO, then you use more of these techniques, then you can forgive yourself on tolerances, which then gives you a higher manufacturing yield, which then gives you lower cost. So at Zimmer Peacock, we don't want to just think about the screen printed electrode. You've got to think about the functionalization, mediators, enzymes. You've got to think about the excitation of it. You've then also got to think about actually the data extraction. How you extract a signal from a sensor can give you better precision and better accuracy. And it's when you just look at a glucose sensor in isolation, you just think about, the only thing I'm going to get this person to control is the screen printing. You're missing the fact that every part of this stack of technologies, you can essentially make improvements. So, it's not good to consider these things in isolation. Screen printing, deposition, excitation of sensor, interpretation of data. These have all got to be thought of together. And in this one, I realized I left out, this sort of idea of microfluidics as well. But this is, if you're making a glucose strip, you've got to also consider the reproducibility of the tolerances in the manufacture of that capillary fill. Now let me dive on a little bit more, which is, I just want to say thank you to Monica, who just said thank you for this. I know there's an awful lot here. I realize it's now 8:28, so I'm going to go a little bit quicker, and my apologies for that. If somebody came to me and said, I want a glucose sensor, what we would do is probably do a pilot run on it. We have the electronics, we have the sensors. What we would do is put the sample on the sensor. We would test the sample on either a clinical analyzer or an existing sensor. So what I'm talking here is about how to kind of get yourself in the USA to what they call a 510K. Show yourself equivalent to what's already on the market and get yourself FDA approval. So how would I do FDA approval? Make a sensor, put the sensor into the meter that we have, put a sample, for example, on the sensor. But I would also analyze the sample using a gold standard, something that's already on the market, or at least a clinical analyzer. So now I'm going to end up with the truth, which came off the clinical analyzer, and I'm also going to send the raw data to the cloud. So I end up with raw, for example, glucose values in my cloud, and I also end up with the value for my sensor and the truth. And what that means I can do is this, that I can develop an algorithm using real data, comparing the real data against the clinical data. If I don't get a good correlation, we can just essentially look at the raw data and find a better algorithm until we get a better correlation with the actual clinical reader. So I've said this very quickly because of the time, but actually this is a strategy to help you much more rapidly to get towards a sort of 510K as they have in the USA. So I suppose it just says that, when people ask us about screen printed electrodes, we're thinking about, well, where do you really want to get to? You probably want to get to some sort of regulatory approval. So, don't separate it all out and say, you just do this. No, we have to be involved in every step of the technology. I'm going to go very quickly, but, if you're making a screen printed electrode for somebody, you have to think about the outgoing quality control. So you manufacture, you do an OQC, we upload our data to Julie, and we yield it, we package it, and we ship it. The minimum we could do, well, not the minimum, everyone does visual inspection, so I'm not going to labor that. Very few people, I think, actually do electrochemical characterization of either final products or screen printed electrodes, but we actually can do that. And we can upload vast amounts of raw data and then let Julie crunch it all into actual, I would say, turn data into information, and then that will, if the quality control manager can look at that, say, okay, it's within spec, ship the lot, and so we've really thought about the data handling behind making electrodes and making glucose sensors, and we can characterize a batch of sensors, heat map them, make sure that everything is within specificity. If it's an unusual sensor, we can actually give it a QR code and end up giving it a sensitivity factor, so you can carry calibration out into the field with you. I understand in this modern day, people, particularly in glucose sensing, don't want to do calibration, so you have to put a bit more effort into it, into the process, let's say. There's a whole page about onboarding as with Zimmer Peacock. I'm going to skip over that. Somebody came to us this week and asked us, I essentially teach in a university, and this is the question. I teach at a university, we make glucose sensors, we have been using carbon print electrodes, and they're looking for, with a silver chloride reference, and we're looking for other sources. Okay, that's quite unusual, carbon printed electrodes. And the reason it's quite unusual is this, that I'm going to just go very quickly and say, if you're using a carbon electrode, you often use a mediator. So the questioner didn't say they were using a mediator. I will assume that they were using a mediator. And the reason that you need a mediator is, the glucose gets to the enzyme, obviously reacts with the enzyme, and we can get hydrogen peroxide. I say this because some mediators will work with a hydrogen peroxide, some mediators will work with the enzyme directly. But if you've got a carbon electrode, then I expect that there's some sort of mediator in the system to help shuttle electrons from the enzyme to the surface. Now, if you don't have a mediator present, then I would expect that electrode to be gold or platinum, but they said it was carbon, so it tells me that they're probably using a mediator. If they're not using a mediator, then it sounds like the carbon they're using has an oxidized surface, and when you have an oxidized surface, then that oxidized surface, these groups it can be kind of redox centers, and these can interact with hydrogen peroxide. So the person asked me, really, can you suggest a carbon electrode for making a glucose sensor? Well, I can. I just want you to know, I was surprised that it's carbon. You must be using a mediator. If you're not, then it must be the oxidized surface that's allowing you to get away with this. So we have some hyper-value screen printed electrodes. You're welcome to buy them. You can buy 300 of these screen printed electrodes for 145 euros, which is less than 50 cents each, and these are pretty good for teaching in laboratories. I will go a little bit faster because I'm running out of so much time. Cortisol. Right, so at Zimmer Peacock we make a whole range of sensors. We screen print, we make glucose, lactate, oxygen, testosterone, which I've touched upon. I'll touch upon pH in a minute, and we also make cortisol sensors. So the person wanted some what's our spec? Well, our spec is this, that we probably have the world's only commercially available cortisol sensor. We've tested it at 25, 50 and 100 nanomolar. We get a nice strong signal. If you want to use this sensor as a wearable, then ZP has a platform for doing this. So we have a platform for helping people with glucose sensor development, and also what I call generally in vitro diagnostic development, but we also have a platform for helping people with wearables. Wearables could also involve CGM, continuous glucose monitoring, for example. So we have a platform, we take our sensors, we put our sensors into a wearable format like this. I mean, you can see this is very much for sort of prototyping, early stage work. Again, we have the app. the app talks to Julian, we can send the data to the cloud. And that really helps us with development and validation, because I think in so many development efforts, people don't know where their data is. So at least with Zimmer Peacock, we know exactly where our data is. It's in the Julie database. So I'm just saying on this one, we have actually developed, just a quick reference here. If you're wondering how big the electronics required for a glucose meter are, this object, which will run a glucose sensor, but will also run this cortisol sensor, this is smaller than my thumbnail. So it's a very small object. We use the same electronics for essentially all of our sensors. So the quick answer is cortisol sensor. We have it. We've tested it at 25, 50, 75 nanomolar. We have a platform called the ZP Accelerator, which will allow us to turn it into a wearable sensor. And then we do actually have the whole sort of electronics stack to send that data actually to the cloud. If you want further information about it, this is a link that I've put underneath the video as well. And with this person, I'm in correspondence with them anyway, so I suspect I'll talk to them and their supervisor soon enough. Connecting to a pH sensor, so sorry, so long, but let's go quick. All right, so at Zimmer Peacock, we're world-class manufacturers of screen-printed electrodes, including pH sensors. If you've got one of our pH sensors, then you need to make an electrical contact on the third pin here and on the right-hand pin here. I did cover this in last week's webinar, where I told people, look, if you want to measure low cost with these pH sensors, just search on pH measuring with Arduino. I said that we had an old page on it. We're not supporting that page anymore, but it's a good start. If you're looking for some electronics at a fairly low cost on this, we also have an OEM solution on this as well. And there's a video. This is last week's video. I've put the link underneath the video, underneath this video, so you can sort of re-find it. Right, so now I will stop. Question number 1. EIS, thanks for EIS. Maybe the equivalent circuit that you're using is the wrong equivalent circuit. You might have a couple of resistor elements in there. You might have to go for something more complicated. Nitric oxide, we've tested it, I think 0 to 80 micromolar. You will have to use the OmniSense package to really use it. The testosterone sensor, we've tested it in buffer, we've tested it in saliva. We'll have to use the OmniSense electronics to run it. Screen printed electrode, it's really, with screen printed electrodes, I think people think of these things as, you know, off the shelf items. No, they're an intrinsic part of your biosensor, and you have to really engage with people to get this right. Glucose strip manufacturing for laboratories, just buy the hyper value screen printed electrodes. We use them, they're fantastic. The cortisol sensor, we have it. I've shown you the data. We have a package of electronics and technology that will get the data to the cloud, and we need to have a deeper conversation about that. How to connect to the ZP pH sensor, middle pin, far right hand pin. Watch those videos about on the ZP website. If you've got any questions, reach out to me. Just want to say thank you very much, and I apologize that this has been 39 minutes and there was an awful lot to cover. I want to say thank you very much to Monica for the lovely feedback today. Thank you to Hitcham, Aftab. I appreciate it. If you're in India, there's a company called Technando. They're really excellent. Reach out to them because they represent us in India. And I just want to say thank you to everyone. My apologies for running so late, and I'm sorry if I've missed some of the details. All right, take care, guys. Otherwise, have a good rest of your day and a good weekend when you get to it. All right, bye-bye.